Welcome again to my course on the discrete mathematics. As we started our lectures, and this is one of the main lectures that we are going to see today. It's about the logics of compound statements. We are going to see some very basic informations that we are going to use in the days to come. So in other words, from this lecture onwards, you are actually into the core subjects of discrete mathematics. Let's see what we have in hand for today. Today we are going to discuss about a certain Boolean logics. Before we go on to this Boolean logics, let's briefly see the applications of this Boolean logics. Yes, the Boolean logic has been used in many different places. Even if you think about starting from the very low level or gate level, even transistor level, we can think about the logics of 0 and 1. And these logics is so easy for us to think in terms of presence and absence of logic 0 and 1, even the presence of signal and absence of a signal in electrical terms. So it's easy for us to map into the system, and eventually we can, with different combinations, perform very complex logics. Yes, of course, it's used in computer programs today, but basically it all started long back. Well then, today this Boolean logic is not only used in computers, hardwares, but also in software terms we use certain logics. Today we have many other places where we use this logical problem to solve. Let's see more about this Boolean logics. To begin with, we are going to start with the Boolean proposition. So what is a proposition? A proposition is a statement that can be either true or false, but not both. So a proposition is a statement that can be either true or false, but it cannot be both. Sky is blue. Yeah, that is a true statement. 2 plus 2 equals 4. Again, that's a true statement. So you can call that as a proposition. 2 plus 2 equals 5. Well, that's a false one, but still it is a proposition. Yes, remember, a proposition is a statement that can be either true or false. Though it's false, we can call this as proposition. Yes, 2 plus 2 equals 5 is false. It's a proposition. There are things that are not proposition. For example, what day is today? Well, it sounds like a question. It's not a proposition. Come here, go there. It's a command. It's not a proposition. How about this one? Think about this. X is greater than y. Is this the proposition? Well, this is kind of fuzzy. It actually depends, right? Even for example, if you are very specific to be, if suppose x is, you say x is greater than 0, if you have the statement x is greater than 0, still you can't rightly call this as a proposition until the variable x takes a value. So if it's a variable keep on changing, you can't call that as a proposition, because depending upon the x, the statement becomes true or false. If x is 1, this can be true. If x is -1, it would be false. You can't have both in one statement. So in that case, it cannot be a proposition. But later on, we will see the areas, the places where we can put values for these elements, and then we can decide whether it is a false statement or it is a true statement. Well, x here equals 7, that is not a statement that gives us a value for true or false. Boolean variables. So since we already defined what is a proposition, we use Boolean variables to represent proposition. Let's refer these Boolean variables to propositions. Say for example, usually lowercase letters starting with P, Q, or S, etc. These are used to represent the Boolean proposition. As the Boolean variable can have one of two values, true or false. Yes, a proposition can be a single variable P, or it can be a multiple variables like P and Q or negation or. Yes, we have P, Q, or. Three propositions are there, three Boolean variables that represents Boolean proposition. And remember, Boolean variables can have only true value or it can have a false value. Let's move on. Let's see some basis of these logical operator. Yes, there are dozens of logical operators that are available, similar to algebraic operators like plus, multiplication, subtraction, division. Yeah, we have all algebraic operations like addition, subtraction, multiplication, divisions. In the same way, we can represent the Boolean variables as well. So here P equals today is Friday, Q equals today is my birthday. So we can see from this we are in fact referring the statement today is Friday to P, and today is my birthday to Q. We will see how we can apply these examples and perform various logical operations. Let's begin with the first logical operator, not. A not operation switches or negates the true value. Say for example, the true value is false. So this negation operator changes or switches its value to true. So we have this symbol is used for negation, and yeah, as you can see here, P, if it is true, the negation of P is false. P, if it's false, the negation of P would be true. Yeah, we do have these operators in the programming language like C++ and Java. It's like an exclamation mark that represents this negation operator. So we already defined P equals today is Friday. So negation of P becomes today is not Friday. Yes, now we have started with the logical operators and we are applying it to the Boolean variables that we have. Let us see the next one here, logical operator AND. So, an AND operation is true if both operands are true, and we have this kind of a cap symbol, and it also looks like A. So, we can have a hint as if it is the AND operation. So, we have P, Q, then P and Q in this truth table. So, when P and Q are true, the output of P and Q is true. But on all other occasions, when P is true and Q is false, when P is false and Q is true, when P is false and Q is false, on all other three occasions you can see the output P and Q is false. In fact, you can represent this by means of a circuit. Say for example, you have a switch. So, let us say we have two switches. So, you have switch P and switch Q, and here you have a lamp there, and you have this battery. So, you have say 5 volt. Well, as you got this switches down here, you can think about a time when the lamp will glow. If P is on and Q is not on, will it glow? No. So, both switches has to be turned on if the lamp has to glow. So, this simple circuit represents the AND operator. Yeah, so in C++ and Java, the operands is ampersand sign, double ampersand. We can use it to have this logical AND operation. So, that is about this, and we already defined what is P and Q earlier. P is today is Friday and Q is today is my birthday. So, P and Q equals today is Friday and today is my birthday. Can you see the AND coming in? Yes, in fact, this logical operator AND is bringing together these two propositions together, P and Q. Let us see more on it. Here comes the next one, which is a logical operator OR. So, an OR operation is true if either operands are true. So, we use the logical symbol, looks like V, to represent the OR operation. Here is the truth table. So, you can notice that when either of the operands, like either P or Q, if they are true, the output is true, and if P and Q both are true, still the output is true. The only occasion in which the output is not true is the time when P and Q both are false. Again, you can represent the whole thing by means of a simple circuit. Let us see a simple one here. Let us say this one. Again, you have a battery, you have a lamp here, and you have two switches. We have P and Q. If I turn on just one of these two switches, will my lamp glow? Yes, definitely. If you just turn on, say, P, or if you just turn on Q, the circuit is complete and the lamp will glow. Or if you turn on both P and Q, still the circuit is complete and the lamp will glow. That's the simple logic. And let's use it in our Boolean propositions. And even in C++ and Java, we use these operands that looks like parallel lines to represent the OR operation. Yes, P or Q. Today is Friday, or today is my birthday, or both possible. As we can see how the OR is helping us to fit in these two propositions. We are going to see how these English terms and logics combine to form these statements. Next comes the exclusive OR operation. So an exclusive OR is true if one of the operands are true, but false if both are true. This is quite unique operator. So it can be true only if one of the operand is true. And you have this symbol, looks like cross, to represent the exclusive OR. Yes, as you can see the truth table, when P and Q both are true, the output is false. Yes, so we talk about exclusive. It should be exclusively OR. Only when either P or Q is true, the output is true. Otherwise, it's false. If both are true or if both are false, the output is false. Why not try to come up with a circuit that represents this logic? Try to figure out a circuit that can bring out this XOR logic or exclusive OR logic. So we often call it as XOR. And here is one equation that equates this XOR operation, that is P XOR Q is similar to P or Q and negation of P and Q. At times these might be useful for us to solve some logical Boolean equations. Later on you will see how you can use it. Moreover, we don't have this exclusive OR operations in C++, but in Java we do have this cap operators that helps us to perform the same task as exclusive OR or XOR. P exclusive OR Q, today is Friday or today is my birthday, but not both. Yes, that's very strict, not both. That's about the exclusive part coming in. Now is that we have seen inclusive OR and exclusive OR. So the question is inclusive OR versus exclusive OR. Do these statements mean inclusive or exclusive OR? Let's see, and now it's your turn to meditate, to contemplate on the things. Experience with C++ or Java is required. Can you think about it? Experience with C++ or Java is required. Yes, you can see the logic where it needs exclusive or inclusive. Lunch includes soup or salad. Same simple logics. To enter the country, you need a passport or a driver's license. It doesn't matter if you have both. Even if you have one, you can still enter. If you have both, you can still enter, which means that this is kind of an inclusive, right? But you can think of other examples like experience with C++ or Java is required. Again, there people might wonder, if you're going for an interview and if you have both experience, it doesn't matter. So in real time, we have to be very cautious in using this exclusive OR. But in logics, these exclusive ORs are very useful, and even in programming terms, we often come up with many logics where we come across these exclusive operation, that is XOR operation, publish or perish. Well, that's like, for example, if you're working as some research institute, and in the research institute they want you to do research and publish your work, and if you're not publishing your work within the time frame, maybe you are fired. So that's something like publish or perish. Logical operators Nand and Nor. Negation of and or these Nand and Nor, and you have these symbols to represent it. It's like a straight line for Nand, and this with the arrow coming down, it's for Nor. So the Nand, P Nand Q is similar to negation of P and Q, and again the P Nor Q is similar to the negation of P or Q. And here is the overall truth table with and, or, Nand, Nor operations. You can see and Nand, they are kind of opposite or complement to one another, and again or and nor, they are complement to one another. Then comes another important logical operator, it's called conditional operator or conditional operation. A conditional means if P then Q, P implies Q. We call this as the arrow as the implication operator, and here is the truth table for this implication conditional operator. So given P and Q, P implies Q. So you could notice the part especially when the P implies Q is false. The only time when it is false is that P is true and Q is false. In that case, your implication, the output is false. So no matter other times whether P is true and Q is true, the output is that P implies Q is true. P is false, Q is true, again the output is true. P is false, Q is false, the output is true. And negation of P or Q is same as P implies Q. So P implies Q, if today is Friday, then today is my birthday. Yeah, for implication we come across with if then statements. That's why we call it as a conditional. P implies Q is similar to negation of P or Q. Again, this might be very useful for us to solve some equations. Later on we will see how we can use these logical symbols and to simplify certain equations. So at times we have to use these implications or negation or and or operations to perform this simplification. Well, considering this part, P implies Q, P is the actual hypothesis that you come up with. This is the premise, this is the antecedent. P implies Q. So again, coming back to this P again, I talked about this as the hypothesis, like if today is Friday, so this is the condition, if today is Friday, that is your hypothesis, that is your antecedent. then the consequent or consequence or conclusion is that then today is my birthday. Yes, so the first part P we represent as antecedent, premises or hypothesis. This implication part, the Q part, we call it as the consequence or the conclusion. Let us see some information about this antecedents and consequence. At times they may not be related, but still the output can be true. For example, if I listen to the class, then I will try to fly to Japan. Well, it looks like F implies F. Yes. So even if both are false, the P implication Q is true. Let us see more on this conditional statement, because it is one of the important part that we have to have a solid basis before we move on. Let P I am elected and Q I will lower taxes. P implies Q. If I am elected, then I will lower taxes. So here you can think about the parts when the implication is true and when the implication is false. Say for example, here the possibilities, there are a lot of different possibilities there. Say for example, if I say if I am elected, then I will lower taxes. Okay, say you are elected and you are lowering the taxes, then the implication is true. But if you are elected and you are not lowering the taxes, then the implication is false. The conclusion or the consequence of what you have stated is not happening, so that is false. But on the other hand, you did not make any promise to lower the taxes, but you are lowering the taxes. In that case, again the implication is true. You did not make any promise to lower the taxes and you are not lowering the taxes, still the implication is true. So that is what we have to understand about this conditional statement. Remember that one place where it is false, on all other condition it is true. When the antecedent or hypothesis is true and the conclusion or the consequence is false, only in that condition your implication is false. Yes. Note that if P is false, then the conditional is true regardless of whether Q is true or false. That is another point that you have to remember. You can keep in mind these are the hints that help you to make the right conclusions when we talk about this conditional statement. So here is a summary of what we have seen in short. We are given with P and Q. The negation of P and Q is also stated here, and then comes the conditional statement, inverse statement, converse and contrapositive. So we will find some relations between these things. So first one is the conditional statement. We know what it is, but this is inverse. Negation of P implies negation of Q, and Q implies P. There are few things that we have to remember, like we know the conditional statement is P implies Q, but this P implies Q is not equal to Q implies P. That is one thing we have to remember. As you can see from this truth table, as the conditional and the converse are not related to one another. But on the other hand, you have a contrapositive, which is negation of Q implies negation of P. So this one, conditional statement and the contrapositive, they are logically equivalent. And then the inverse and converse, they are again logically equivalent. Yes, so these are some of the truth table that we have seen today, some of the logical operators we have seen. We saw what is a preposition. Yes, what is a proposition? We have to understand what is a proposition. We have to understand what is a conditional statement and what is the implication represents, and all their truth table. Try to understand the truth table. Don't try to memorize these truth table. They have a logic behind it. Try to understand the logic behind these truth table. And in the next lecture we are going to continue with this same thought of logics of compound statements, and there we are going to see more examples on how we can relate. And there are a few more statements like conditional statements, biconditional statements, or the things that we are going to see in the coming next lecture. So until then, I wish you enjoyed today's lecture, and looking forward to the next lecture. Until then, goodbye.